Hello, am I audible? Okay, is it visible? Am I audible? Okay, so let's start this section where we'll be seeing the thermal selection of the machines. Okay, so what is the importance of machine power rating selection? Is there any importance? So is there any importance to machine power rating selection? What if you are not choosing the optimal rated? Say you need a motor of say 500 watts, right? But you are employing a say 1 kilowatt motor. So what will happen? You can talk here also, don't worry. So what will happen then? Yes, it will take up load. It will do the work, but you are paying for 1 kilowatt. That means the cost has increased, right? And then the efficiency will be decreased. Why? Because if a motor is rated at 1 kilowatt, that means it will give you maximum efficiency near about to this rated power, right? But if you are using at half the power, then its efficiency will definitely be less, right? So that is the two important things. And just don't think of this cost only. You might think that okay, it is a single motor, so one extra cost, so what does it matter? But no, if you think that it is single motor, you are wrong. Think that you are employing 500 such motors. You are employing 500 such motors, so you will incur double the cost, right? So if you incur double the cost, your tender which you are giving to some other company will be increased, right? So if you are giving more money in the tender, then you will lose the tender and your company will not be operating, right? So you need to find the optimal rating that is required. And what if you have 500 watts and you are giving only 400 watts? Say this is a lift. A lift needs, a small type of lift needs 500 watt of power, right? If you're implying 400 watts of power, what will happen? It will take up the load up to some extent because the difference is low, but overheating will be happening, right? And then efficiency will be down because you are running the motor above the rating, and there are chances of failure also, right? So if 500 watt, if is the its thing, you can go for hardly 600 watts motor. That is good enough, right? So less efficiency if underloaded, failure if overloaded. Associated power equipments like converter, etc., may get affected. So who is driving the motor? The power electronic controller. right? So if you are using 1 kilowatt system instead of 500 watt and your power controller is also 500 watts, then is it not a mismatch? It will affect the power electronic item, na? Just a second. Say it is a power electronic controller of 500 watts and this is a motor of say 1 kilowatt, right? Now for 500 watts it is working perfectly. Now say suppose if the load is increasing say 750 watts, will there be any problem with the power electronic controller? Yes, obviously, because you have kept only 500 watts. And if you're using the cheaper ones like the Chinese ones, then it will get busted at after 500 watts only, right? Because for the Chinese electronic controllers, the overload capacity is very, very less. So that's the reason why their products are very cheap. So if it is rated 500 watts, you should obviously use it below 500 watts only, because power electric controllers, depending upon the cost and the quality, it might get destroyed also. The costly if overrated, right? So temperature rise in winding core due to machine losses. So if you are underrating the device, first of all, it may fail, right? And if you are overrating, the efficiency will go low. So if the efficiency goes low, the copper loss, iron loss, frictional loss in bearing, windage loss, everything will increase, especially the copper loss and iron loss. Then the machine insulation classes. This window is disturbing very much. No, what to do with this window? Still could not get it. Okay, so this is a formula. Just a second. So this is a formula to calculate the temperature rise due to a operation of a motor. So what is theta SS? Theta SS is the maximum temperature rise under steady state. Theta naught is the rise at the beginning of a heating cycle. It is the time constant, that is the tau. So see, it is an exponential type, right? E to the minus t by tau. So temperature drop during cooling is this formula. So this is an absolute model. It is not an empirical one. It is not empirical. Means it is calculated by maths direct. You can get the results if you put the values here. So classes of motor duty. This is very, very interesting. So say, first of all, we are taking as continuous duty motors. Like in the summer season, for how much time the fan is on? For how much time the fan is on?
24 hours.
I think it's already for 24 hours, right?
Mm.
Hardly we get it off. So if you are there in the home, it will keep it always on, right? So it is a type of continuous load, right? So motor operates at constant load for a duration long enough for the motor temperature to reach steady state value. Means what if the temperature keeps on rising in this fan? Then the windings will burn out, right? So thing is that it has to dissipate the heat also. So that is why it can run for long time. So examples are compressor, fan at fixed speed, centrifugal pumps, like the water pumps. So that's an example. We cleared the screen. That's an example of a fan type load. Then this is the compressor type of load. Just a second. I should have been rotating. So this is a compressor type of load. This will rotate and the water will go inside. This will get pumped out through this pipe. That's a centrifugal pump. This is a short time duty load. Means what? Just like a crane.
Mm.
So crane is what? It will be on for a short time period, which is less than the heating time constant of the machine. Means just for some time it will be on and then it will go off. Just a simple crane. Then it is intermittent periodic duty. What is this? Refrigerator. How does it operate? It has a thermostat, right? It has a mainly it has a thermostat. After reaching say 10 degree Celsius or minus whatever the preset value is, it will get switched off. So it is what? It is on for some time and
And
then
off for
it goes
some time.
off. Again it is on for some time. When the temperature increases beyond the predefined limit, again it goes off, on and off. So it is called intermittent duty. So duration of running period is not long enough to raise the temperature to steady state value, not the rest period long enough to cool to ambient temperature. I've already mailed you these slides, right?
Yes.
I gave to Deep, I think he already forwarded
Yes.
it. Right? So it's the refrigerator, the manipulator arm. Then we have the intermittent duty with starting, periodic duty with starting. So this is a type of graph where you start and then heating during starting cannot be neglected. Operation and rest periods are too short for reaching steady state temperature. So once it is started, it heats up and then the operation happens. During the operation, the temperature goes down a bit and then finally it is going down, but it is not reaching the zero state. It is that some temperature is definitely there. So it is like metal cutting, drilling, forklift. This is the forklift truck. So this is the drill. So when you are drilling, what you have to put here? What you have to put in this zone? I think you have a type of fluid, a liquid type that is whitish in color to keep it cool. To keep it cool, you have to include some type of fluid. I think that is a type of water or something. So they have it cooled here. Now this is the forklift truck. Okay, then here is the intermittent periodic duty with starting and breaking also. So that's a big difference now. We have to start also and to break also. Right. So what is this? This is starting time. Then this is the running time. Running time, the torque is a bit less. The starting time, the torque is very high. And then this is the breaking
Sir,
time. Yes.
sir, can you explain the previous slide? Fourth number. Intermittent with a starting. Intermittent with a starting. Yeah.
Yeah. Intermittent with starting duty. So just let me clear. Okay. So just think of this drill. So when it is starting, why did it pause? Yeah. So when it is starting, say the heat is very high, is it not so?
Yes.
And then when it is going inside, then it is a bit lower heated, and then it doesn't have to break. It is just resting after the operation, after the drilling has been done.
Yes.
So that's it. And same thing is with a forklift truck. See, when the person is just lifting, it requires very high torque, and then the demand for torque decreases, so the temperature also decreases. So where is temperature coming from? Temperature is coming from actually the current factor, this I square r loss. First of all, the I square r loss in the motor, right? If it's a motor, it will have some current drawn,
Yes.
right?
And
And
I
it will
square
have some I
losses.
square r losses. Now this current is governed by the load torque, the requirement of the load torque, right?
Mm. Yeah.
So the pattern of the load torque actually says the pattern of the current, right? And the pattern of the current says about the heat. So the more the heat, the higher is the temperature. Accumulation of heat will give more temperature.
Yes.
Okay? So that's the point. And so these points are being followed. See, these points are being exactly followed. So when it is starting, it is taking huge current. So the I square R loss is high. So the temperature rise is very high. And then after it has reached some type of operation steady state, then it is going a bit low because the requirement of load torque during running condition is lesser than the starting. And then when the operation has gone down, the temperature goes down slowly. Okay. And now say what about these types of loads? These types of loads are like electric trains. When they will start, they will take a huge torque,
Yes.
right? And after it has started, it will require a lower torque to run it. Is it not so? The starting torque is definitely greater than the running torque. And then when the station is approaching, it will go for regenerative braking.
Yes.
So during the regenerative braking also, the torque is reversed, right? The torque is reversed, means the generator torque is reversed, but there is a current flow from the load to the source, right?
Yes.
So it will first increase and then the temperature will keep on decreasing. Again at this point, the train will start and it will again keep on decreasing for the rest of the time. So this is called intermittent periodic duty with starting and breaking, right? So is it okay?
Yes, sir.
So classes of motor duty, continuous duty with intermittent periodic load and all these things. Then determination of motor rating from thermal point of view. Why is it important from the thermal point of view? Because after all, you need to keep the temperature of the motor at a safe limit, right? You cannot allow the motor to be heated just like flames, right? So you need to keep the temperature lower, as low as possible. So you have to classify as per the duty cycle that what type of, see, this duty cycle is not that of the D type. It's not that like that power electronics 4 quadrant choppers. This duty cycle is of the load, or how much time the load will be on and off. So motor selection for continuous duty, maximum power demand of load is determined. Say the load requirement is this much high, and then it falls down to this much, and the running load is this much. So this is very much evident for the EV bikes, electric vehicle by e-bikes. So say two persons are sitting on a bike, then just imagine the amount of torque required to just start it from 0 to say 10 kilometer per hour. Just can you think how much current it will take out from the battery? Say it might be 100 amperes, right? But once it has reached a 10 kilometer per hour range, then what about the rest? Say from 10 to 40 kmph,
Yes.
the requirement of running torque is lesser now. So this is called running torque. This is called the starting torque.
Starting top. Yeah.
So for the starting torque, the requirement of that is very high, but this for the running torque it is lower. So that's why it will require lesser of power. But if you are say this takes but 100 amperes, so this is the peak, right? That is the peak current, and say in the steady state it needs 25 ampere in the steady state. So just imagine you have made a battery there, you have designed a battery which can give only up to 30 ampere. So tell me, will your vehicle start with two people Will your vehicle start?
No.
Yes, it will start, but uh, but the surface has to be like this, right? It cannot be flat. If it is flat, it will not be able to pick up that 100 ampere, right? So that is the essence, that if you have to start, you have to have this peak rating in your motor side also, and in the battery side also. Means the entire system must be able to give this peak rated power, right? Then the next available higher power motor is selected, right? Say, okay, can you tell me what is the power rating required to pick up 1% in an electric vehicle? What is the power rating required to pick up 1%, to pull 1%? It's 200 watts. So every electric vehicle will have this 200 watts BLDC motor fixed in them. It's called in-hub motor, in-hub BLDC motor. Is it proportional for every person? No, this is approximate. How can it be proportional? So the if you're much more lighter, it will draw in lesser power, so your battery mileage will be more. The approximate, this is the 200 watts is that section for which one person needs. Guys, don't please talk. So motor selection for fluctuating and intermittent loads. So how do you select a motor for these types of loads which are intermittent, like this? How do you do it? Any idea? See, this is the load torque, right? Load torque is given by the generated torque. The generated torque gives the load torque, drives the load torque, right? Can I get some replies over here?
Yes, sir. Yes, sir.
So if TG is driving TL, then TG is governed by TG proportional to phi I and cos phi if it's an AC motor. But basically it is a function of phi and I. So why it is phi? Phi is the field flux and I is the armature current, right?
Armature current.
So basically if you are taking hold of this phi f as constant, so forget phi f, then TG will be proportional to IA only, some type, right?
Yes.
Then this IA will have a current pattern similar to this, right? So if you are going to buy some type of motor, then how will you buy it? Then its current rating must be like the pattern of the load torque only, right? Means it must be able to pass say 100 amperes at starting and say 25 amperes at steady state, right? So we can we have an RMS value of this thing, like we used to have for currents, right? If we have this type of current, sinusoidal current, then what we used to take the RMS value, right?
Yes.
So we have to take an RMS, so that is called the load equalization. Means you are trying to manipulate these type of fluctuating loads into a flat load. Are you getting it? You are trying to manipulate, you are trying to have a mathematical form to have a single motor rating which will handle all the fluctuations of this type of load. Is it okay?
Yes.
Okay, so this method is applicable for classes 3 to 8. So you will have already got the slide. So, sorry for this window. Till now I am unable to fix it up. Okay, so equivalent torque and power method is this one. Okay, so variable motor current can be replaced by an equivalent current which produces same loss in the motor will act with actual current. So this is the principle for RMS calculation. Yes. So motor loss is a function of fixed loss, that is a core loss plus friction loss plus variable loss which is the copper loss. This is the I square R loss. And coal loss, I think everyone knows, that's the same thing as of a transformer. Then this is the arbitrary fluctuating load. This is a model. Say if your model is consisting of this type of load torque, so this is the value of I1, this will be the peak, right? Is it not the peak? And then you have again a low. So say your motor your motor should pass this peak current at least for some seconds,
Yes.
for some seconds. And but if you keep the motor rating up to this also, then also it's a loss. Say this peak needs a power of say 2 kilowatts, right? But this needs a rating of say 1 kilowatt. So which motor will you try to buy? Tell me. And this is 1.5. So the essence is that you will try to buy a motor in between 1 and 1.5 kilowatt that is able to handle the 2 kilowatt peak load for some time, right?
Yes.
So that's the reason why we are going for load equalization. We will take the values of T1, we will take the values of I1, similarly for I2, T2, all these things, and then we'll fix it up of load equalization type of thing, which will have the RMS values. So we are trying to have a lower cost of motor, optimal cost of motor, optimal rating of motor, which will be able to handle this high amount of load for at least some time. Say 2-3 seconds, it can handle 2 kilowatt. That is also good enough, right? But the main RMS rating of the motor is only 1 kilowatt, right? So the cost will be lower instead of having the full full kilowatt as two kilowatts. So this is the formula which you can see here. So equivalent current IEQ is given by, this is the constant loss and this is the variable loss, is equals to, yeah guys, please see to this. This is the constant power loss plus I1 square R T1, that is I1 value for T1 seconds. Then this is the PC again for I2 for T2 seconds. Similarly for all the losses. Now, how will you find it out? So PC, if you take in common, you end up doing this calculation, and so IEQ will be this. So this is the equivalent RMS current for which you should find a motor in the market. So say this is 5 ampere. Suppose this is 15 ampere. Say. So which rated motor you should find? Say 230 volt. Uh, will you go for 15 ampere if it is not there? Say for this type of motor, 15 ampere 230 volt motor, you go to the market and the market has the following varieties. Say which one will you take? Will you take this?
No.
Why? Because it is underrated.
It,
It will not be able to
yes.
handle the peak load also or the steady state
A starting torque. Yes.
load also. So this is rejected. Will you take this?
We'll consider, but will not.
Obviously, you can take this. You have lots of money, right? But majority of the people will not be buying this because this is overrated motor. Instead of 15 ampere, you are taking 25 ampere. So that's called overrated, right? So you can do it, but it's a loss of money. So the most economical is this motor, 230 volt, 16
Okay.
ampere, right? So you have to find the motor rating in such ways. So motor rating will come in VI cos phi. Why is the motor rating in watts, and uh, why the output of a transformer is in VA? Motor rating is in watts and the transformer rating is in VA. Why?
Because transformer rating doesn't depend on cos phi.
The
It's for
rating depends upon the type of output you want. A motor will give you a physical rotational output, that's a mechanical output which is real. So real is watts,
what
right? And electrical output is given by a transformer, right? So it
voltage
consists of
ampere.
the real power also and the reactive power also, right? So it is in VA. Okay. So the ratio of I max and I rated should be less than overload capacity of the motor. So the overload capacity of the motor, say it is 1.5 and the motor rating is 500 watts. So how much of overrating can it happen? How much of overrating can it take? This is continuous power. This is continuous power. And this is 1.5 times it can be overrated. It is written on the nameplate, say. So how much maximum power we can go for it?
This is
There is definitely 1.5 into 500, right?
it's 750.
1050 watts,
750.
right? But this overload can be taken only for a less amount of time. So DC motor normal overload capacity is 2 times. That's a great thing, right? That's very obvious. So that was the end of unit 1, right? And whatever the torque equivalence will be coming in the same style, right? So T equivalent will be equals to T1, that is the amount of torque present for T1 seconds square, then it is T2 square, T2, and finally divided by the time, and this is the square root. So this is the RMS, root mean square, right? So this will be the torque rating of the motor. The torque rating of the motor. This will be the power rating of the motor, equivalent power rating. So are they two different? The formula seems to be the same one, but are they two the different? Obviously, it's different. Why? Because a motor may be of the same power, but it might not give the delivered torque, because power is equals to T into omega. So it might give you the a greater speed but at a lower torque. So that is also not acceptable, right? First of all, the speed matching has to be there. The speed matching has to be almost of the same or divided by the gear ratio, right? And finally, the torque matching has to be there. The torque matching has to be there. Say it is of 5 Newton meter maximum, but the load torque is a 50 Newton meter. But they are both giving at a power of 100 watts. So can you do it? And the machine start even? No, right? Say this is the load torque and this is the generated torque. So it cannot start, but the power rating is same. The load needs 100 watt and that also is giving 100 watts, but the speeds are different, right? So first of all, you have to look at the speeds, that at how much speed it is required. Speed. Second of all, torque. Let me So first of all, you need the RMS current equalization. Then you need the speed matching. Then you need the torque equivalent. Then you need the power equivalent almost. Finally, it will be done. Right. So these are the factors on which the motor power rating has to be decided for a particular application. Say you are trying to go for a crane type of load, and what you are employing a shunt DC machine? Will it be able to do it?
No.
Say the crane needs to pick up a power which is equivalent to 10 kilowatts for 1 second. So will you be going for shunt DC machine, and will you be focusing on the continuous power rating?
No. Intermittent.
So you will be focusing on the peak power rating, right? You will be focusing on the peak power rating, the overload capacity, and because you will be employing it for a very small time, 1 second. So that's the good thing, right? So you will get the motor at a lower cost also. But the associated power electronics item, if it is there, it has to be also rated for such high watts. So that is also another concern, right? Okay, so that was the end of the slide. Any doubts till now? Any doubts till now? Okay, you're welcome. Is there any doubts from here? Okay, so let us end the class now. 11:40. You will have your internals on 24th, I think. When is your internal, guys? Where is your
20,
internal?
24th.
It's 24th, right?
Yes.
So today is 23rd. Okay.
23.
So questions will be coming from unit 1 only. So please go through all the slides that has been provided to you on your WhatsApp group, I think. So from there only everything will be coming. So best of luck for tomorrow. Okay, so see you after the internals.